Okay, so we're gonna try this. This is gonna be lesson 6.5 I, meaning on your syllabus it's noted that this is the first section of 6.1 or 6.5. Okay, 6.5 I, and the title of this entire section is volumes, and we'll break it into at least 2 days worth. I think 2 days for the first section and 2 days for the second section. So I bet we spend 4 days in this 6.5. Okay, it's quite a bit. We've just looked at the idea here. The idea is that though my function may change the shape of the solid, I could still find its volume. Okay, if it's not just a regular old geometry shape, I know that I could take the area of the base times its height, typically, right? So pretend like I'm dealing with a cylinder, and we started here, and I want to find the volume of said cylinder. Well, I just laid it on its side because I want to say that this is from A to B, right? If I cut this cylinder, these are called cross sections, right? And I opened it up and I looked at it. That's the cross section. The area of each cross section in this case, because it's circular, would be pi r squared, right? And so all I would have to do there to find the volume is to take pi r squared times the length of the base, which would be b minus a on the interval from b to a to b. Is this making sense to you guys? Okay. So this is not out there. This says volume of any kind of prism. You learned this in 8th grade. Volume of a prism is area of the base times the height. Area of the base times the length of the shape. Big B, little h. Is this ringing a bell? I taught some of you in 8th grade. This should ring a bell. Everybody good with this? Okay, but what if my solid, my three-dimensional figure, looks more like a loaf of bread than it does?
Man, I'm gonna suck at this for drawing. Like, I can't draw.
Okay. What if my shape looks more like a loaf of bread than it does a cylinder? Well, I'm still going to have the same idea. I'm still going to integrate from A to B, but the area of each shape is going to be defined differently. It's going to depend on the function that we're looking at. Okay? More to come on that. Each problem will tell you how to define your shape. But the idea here is still the same. The volume is the summation of all of the little cross sections. Okay? And we want to cut it into infinitesimally small pieces so that it's accurate. This shape cross section is probably, if I cut it right here in the middle, y'all know how this works. Nobody likes the heels, right? Say you're going to go toast some bread. Visualize toasting some bread, right? You throw the heel pieces away at the end, usually. Y'all eat the heel pieces?
No.
Y'all weird?
I don't waste them.
I make his sandwiches out of the heel because he doesn't care.
Okay, well, so for the people who don't care, they can have the heels. The rest of us like these middle slices, right? They have less crust. It's a bigger slice of bread. As we taper off and we get to the end piece, it's a different size. That's why the volume is more accurate if we take infinitesimally small pieces, because each piece could be different based on the size of the function, based on how the function is working here. Does that make sense? If I cut this loaf into cross sections, the heels area versus the area of the bread in the middle is going to be different. So the smaller the cross section, the more accurate, right? That's what we want. So we take it from being a summation of all of the area pieces and we turn it into an integral. It's smoother, it's better, it's more accurate. And so we integrate the area function on the interval from A to B to find the volume of the solid. And that lets us add up every single piece, no matter what its size. Okay. Questions on that? Anybody? Okay. So the first example here, example 1, is just a derivation. Example 1, it says, show that the volume of a sphere of radius r is v equals 4/3 pi r cubed. V equals 4/3 pi r cubed. We're supposed to prove that using this idea. And we're talking about a sphere. And they have drawn for you a sphere on page 519. This is in the middle. I don't have these drawings screenshotted. I should have thought ahead and gotten there, but this has been that kind of week for me. So, looking at kind of the sphere shape that they have cut out for you, they're saying the area, so they got a sphere and they've got a cross-section cut here, and y'all have to just forgive my badness. The area of each cross-section is going to be circular. Would you agree with that?
Yeah.
Can you imagine if you cut a sphere? We just watched those cutting videos. You got a picture, a sphere, and we cut it right down the middle. The area of each sphere is going to be found by using pi r squared, the area of each circle. Okay. If this is a sphere, then we're going to have to come up with a function for this business.
For each piece or just one?
Okay, so that's a great question. We need a function for the area. We know that in this case, area is going to be pi r squared, but what's r?
It's different, and it's is this a 45?
Okay, so he said it's different. Let's stop right there. He said it's different. The radius, if I cut a cross-section here and measure from the x-axis to the top of the sphere, that r is different than if I cut it right down the middle. This r is bigger. And if I just cut a very tiny sliver on the very end, that r is tiny. So we've got to account for that somehow. We know that the radius is changing as a function of the circle. Can you see where we're going with that? Okay. And so in the middle of their sphere on this page, they've drawn something pretty neat. They've drawn a right triangle, and they've connected from the origin to the outside of this triangle, and they've called that piece R. That's the radius.
It looks like a 45, 90, but is that like confirmed?
No. So the distance between that point on this sphere and the y-axis we could call y, and the distance between that point on the sphere and the x-axis we could call x. And so we can come up with a function for r, this guy right here, because he's changing. He's changing as the circle, as we move within the sphere. Okay? Y varies with x, right? As x changes, we see a difference in r. Okay, so let's say what r might be. How could we find that relationship? How could we define it? Pythagorean. Pythagorean. Do you see the right triangle? So the relationship here is x squared plus y squared equals r squared, right? We want to integrate with respect to x in this case because we're saying that volume is going to be the integral of area, ax dx. So we want to integrate with respect to x, which means we want our equation to be in y equals form. Okay, so we have this function, this relationship here. We want this to be solved for y so that we can use it in our area function. Okay, so what are you saying?
The square root of r squared minus x squared.
Good. So the y is equal to the square root of r squared minus x squared. Okay. The radius that we're saying is changing every time is our y value within this circle. Because I'm not talking about the radius of the sphere. That would be this r. I'm talking about the radius of each cross section. That's going to be the y value here. Can you tell? So instead of area being pi r squared, which would have been this little r over here, we're actually going to say this is pi y squared. So this r is not the radius of the sphere, but the radius of each cross section. Can you understand? Like, y'all look at me. That just got deep. I'm not saying area of a circle is pi r squared, but we're not talking about area of the sphere. Or the radius of the sphere. We're talking about area of each cross section. And each cross section has a radius of y. So the area function that we're actually going to use is pi times what was y squared? We could leave it as r squared minus x squared. If we want to substitute in here, we don't have to take its square root. We can use y squared as r squared minus x squared. There's our area function. And where are we going to integrate it from?
From 0
How?
to x.
Okay, how far out is this point and this point? How far across are these?
It's negative r to r.
Negative r to positive r. Yeah, this is a sphere. And so I'm talking about its diameter. Its diameter is measuring from negative r to r. That's how far we want to take these circles. Okay, so those are our limits of integration. So we're going to have volume is equal to the integral from negative r to r of our area function, which is pi times r squared minus x squared dx.
Pi is a constant. Could we pull that out of the integral?
Pi is a constant. We could pull that out of the integral. Sure. Anybody see anything else that would make life simpler? Symmetry. You're the one that always catches that. Okay, so this is a sphere. It's perfectly circular, which means it's symmetric on its interval from negative r to r. So we could use 2 times the interval from 0 to r. Anytime symmetry helps, I say let's use it. So we actually have 2 times the integral from 0 to r of r squared minus x squared dx. And now we calculus. You understand this setup?
Why?
Why what?
How would this be accurate to this one specific sphere, like the volume of it? What if this is the area of a circle to like a completely different area of a different sphere?
This works for all spheres because we're using r.
So how does this circle that we've chosen, how does this show us the volume of this entire sphere when it could be like a different part of a bigger sphere?
Because we said that the circle's radius is y. As y depends on r.
Okay, that's the connection.
Mm-hmm.
Okay. I didn't see how it connected to the bigger sphere. It could just be like any circle.
Did y'all see that? The circle's radius is y.
Okay.
Period. As y is a function of r and x. Okay, so bigger sphere, bigger y. All right, let's take this piece of information, v equals 2 pi times the integral from 0 to r of r squared minus x squared, and let's integrate that. Why does it say 2 pi? Because I use symmetry. Okay, that's why we're from 0 to r. Just making sure we caught that. So r squared, that's a constant. That's a constant. R being the distance around from the origin to the outside of the sphere, that's not actually going to change. R is a constant number. That R is constant. The y value R that we used for area of each cross section, that is fluctuating, right? But this R is maintaining its constant radius all the way around the sphere. So when we integrate a constant, what do?
We just add it out.
Put an x on it, right? So this integral is going to be 2 pi times r squared x minus x cubed over 3. Yeah. On the interval from 0 to r. You'll see where this is going? So we have 2 pi times r squared times r minus r cubed over 3 minus, open parentheses, r squared times 0 minus 0 cubed over 3. So we did indeed zero out that second half. Thank you, symmetry. So in the first half, in the simplification, we have 2 pi times r cubed minus r cubed over 3
Common denominator.
Okay, so 3r cubed over 3 minus 1r cubed over 3, 2r cubed over 3. So 2 pi times 2r cubed over 3. And the 2 and the 2 can make a 4/3 pi r cubed.
That's like the formula.
That is the formula. That's what we just did. We proved it. Ta-da!
I forgot to.
You do like or you don't?
No.
Oh, come on, Seth.
It's not so bad. You really have to wrap your head around what we're doing. Then after that, it's not so bad. Okay? My former student, whom I love dearly, cried her tears because she said, I cannot see the shapes. That's the hardest part, is understanding the shapes. What are the shapes that we're talking about? Okay? Any questions on that one? Rico, you good?
Yeah.
Okay. Rico, in the days that you've been gone, I think we've covered 17 lessons.
Wow. It was one like 20-minute lesson.
Good. We did stuff yesterday. I just didn't record it because it was a review. All right, example 2. Example 2. Here we go. This one says square cross sections. Square cross sections. So the base of solid S is a circle of radius 1. Okay, so what we've got is a circle planted on an axis. Circle. Put it down. The radius is 1. The radius is 1. So what that means is your measure across in X goes from -1 to 1.
It says base, so shouldn't it be along like the X and Z axis instead of Y? So like
No, planet. Yeah, the Z-axis is coming out at you.
Yeah, and it said base, so that's like the flat part, right?
No.
No.
Lay your base down on the XY axis. Let the solid's third dimension come out at you in the Z-plane. For this solid, the cross-section slices perpendicular to the x-axis. Okay, so this matters. So it's coming out at you in the Z-plane, right? We are cross-sectioning perpendicular to the x-axis. When this tells you which axis you are going to be perpendicular to, you solve for the other letter. Okay, so if it says perpendicular to the x-axis, then we need our function to be y equals. Because I'm going to be, if we're cutting perpendicular to the y-axis, now what's changing? Imagine. The length in x is changing as a function of y. But if I'm cutting it in the y perpendicular to the x-axis, what's changing? The heights. Right? As x changes, if I cut it out here, let's get some pictures going here. If I cut it out here, that's different than if I cut it here, right? The y varies with x. So we want a y equals equation. Versus if it said I'm cutting perpendicular to the x-axis, then I would be cutting it here. Perpendicular to the y-axis, I'd be cutting it across, like laying them down like this. So what's changing? The x with respect to y. Can you understand the difference?
So it would give us 2 different numbers?
It'd give you 2 different numbers. It shouldn't.
Yeah,
It shouldn't. If it's a sphere, it shouldn't. You should get that because volume is volume. Yeah, I can't remember. I think that it wouldn't matter. But it's a lot easier.
Because of the terms, that's more.
Yeah, because you're still finding the volume of the solid. But it varies with what's changing and the ease of finding your area function. Okay, all of that to say, if we're cutting perpendicular to the x-axis, then we're going to be, what I take from that is I'm going to be dealing with dx. Every time it tells me what axis I'm cutting perpendicular to, that tells me what letter to use. Okay. Now, it says these cross sections are squares.
Please pardon for this interruption. Teachers, if your student
Okay, listen. This is important. The cross sections are squares. Okay, so we need to know what's the area of the square that I get by cutting this guy in a cross section. Can you imagine it? So this is a square. I just laid it down, right? It's coming out at you. So imagine its cross section looks like this. What is the base of this square, which is this piece here that you see on the circle?
Oh, it's y.
2y.
2y, yeah.
2y.
I can't imagine a square in
Because
this.
it goes above and below.
I get it. I don't know why.
So like the square is
It's
bigger
wide,
than
wide.
the actual.
Wait, why are we doing this?
That's a rectangle. It's not a square.
Yeah, there's a picture on the next
Okay,
page.
now I
that
get
might
why
help
she's gonna
visualize
have
it.
Okay, turn the page. Everybody turn the page.
Oh, so it doesn't really.
Oh, we're
fit.
finding this.
It's not even a circle though.
It's not, it says the base of the solid is a circle.
Oh.
So it's not a sphere.
I see what you mean.
It's a circle base, and it's sat down on this axis. And then they cut it into cross sections, and the cross sections happen to be squares. Okay? Can you tell?
Squares are nice.
Okay. Can you tell that the cross sections are squares? Look at the picture that they put on page 520. Yes. Okay. So what we need to be able to do, the hardest part of this is finding the area of the square. Well, the square is area side squared, right?
So 2y.
Always side squared. Side times side. Always side squared. Okay? But we don't know what the y value is here. The y value is changing with x. So we need that circle radius idea again. Okay?
We have a number now. It's 1.
The radius is 1, right? The radius is 1. My y value and my x value and my r value are all here. Y is going to be, because we're dealing with this Pythagorean triangle again, y is going to be equal to the square root of 1 minus x squared, 1 being r. We're using x squared plus, or equals 1 squared. So y is equal to the square root of 1 minus. Everybody okay with that? Okay. That's the value that's changing. So the side of the square, though, because this is only 1y, the side of the whole square is 2 of these. Do you see how I need 2 y values to accumulate for that whole, or to count for that whole base? So the area is going to be 2 of the y values squared.
So we can get rid of the square root side.
No, no, because it's 2 times the square root of 1 minus x squared squared. This is your area formula. Questions on how we came up with that? We got about 5 minutes to wrap this one up. When I square a product, I square both pieces of the product. So this would be like 2 squared, 4, times the square root of the stuff squared, which is going to be 1 minus x squared. There, it got rid of it. I would distribute the 4. We want to get this as simplified as possible before we go into our area function. Into our volume integral. Volume is always the integral of area. Now we have an area function. Again, the hardest part is figuring out what's happening here. Recap. I'm looking at squares. Each side of the square is laid over on the y-axis here. There make 2 y's to account for one base. So I would have 2y squared. Y can be found using a Pythagorean relationship, mostly because I'm dealing in a circle. And the radius of the circle is 1. So y is equal to the square root of 1 minus x squared. 2 of those get squared. There's our area. Yeah? Okay. We don't have any idea that this thing is symmetric. We do know that its base is a circle. Okay? So I think we could probably use symmetry here. I would set up with negative 1 to 1 area x dx. And I think you could go 2 times 0 to 1. Because its base is a circle, you could do that. It's symmetric. It is. Facts. Circles are symmetric. So we can go 2 times on the integral from 0 to 1 of 4 minus 4 x squared dx. No, it's not hard. It's just getting to this point that makes us tearful. I get 16 thirds. (24 thirds minus 8 thirds). Yay! Go us. Wow. Do you understand? Like, I know that it's hard. This is the most difficult thing we'll do all year. But do you understand what we're doing? That's my main question. Yes, yes, yes. Okay, yeah, we can start there again.